All right, welcome back. So today we are continuing into compilers, and we're going to actually start looking at how we translate this intermediate representation language that we went over last time into Intel x86 assembly code. It's going to be what a compiler does. It translates one programming language into another. So this is broken down into 4 sections. We're going to talk about how functions are implemented. That's going to take a little bit because there's a lot of details to go into there. Then we'll do arithmetic, branching, and finally pointers. And I've given lots of time for that because while the translations, after you write them, are pretty simple, understanding how they work and what they do is not trivial. It's pretty tricky. So today we're going to start into functions. I've also put the first part of the code generation project online. And there'll be 3 parts to this code generation project. You'll submit them all separately. I'll talk about this more when I get to arithmetic, but basically, if you wanted later sections to work, like if you want arithmetic and branching and pointers to work, you have to get functions right. But I'm going to design the project in such a way so that you don't have to do that. You don't have to write. You don't have to get functions correct in order to get the rest of it correct. You can't actually call your main method without your function project working correctly. But I'll talk about that more when I get to CodeGen 2. So these will be submitted as separate projects, separate repos for each of these 3, although you could, in principle, combine them all together and have a single compiler for the language. I've also factored out all of the information about the code generation process into this handbook, which applies to all of the projects. That way there's just sort of less repetition in each CodeGen project. And I've given these as reading assignments. So they're not that long, but you can use this as a reference when you're writing your compiler, writing your code generator. It'll give you tips on what the actual assembly code looks like for the various simple IR constructs. It'll show you what each function that you have to implement looks like. So these are the listener functions for your ANTLR parser, and which project they're in, which ones are given. And it'll give you tips on how to generate code for each of these constructs in the language. So remember, the ANTLR parser gives you a parse tree. The ANTLR tree walker executes one of these listeners for each construct in the simple IR language, and then you'll write code that will spit out assembly code. Yeah. They're graded as 3 separate projects. They're 3 independent projects. So you could put them all together and at the end if you like. But yeah, I don't want you to be penalized. If you don't get CodeGen 1 right, I don't want you to be penalized for CodeGen 2 because they do have dependencies on each other. Okay, so we'll talk about this more as we go over the assembly or go over the compiler project. All right, so questions from last time, questions on the kind of basics of our tool chain, how the tool chain works, where the compiler fits, on the intermediate representation language, simple IR. Bless you all. Bless you. Questions on any of that? Okay, questions on the homework? Everyone able to write a simple IR program? I know Fibonacci is kind of a little bit painful to write, but any questions on simple IR? Yeah. Oh, yes. Oh, my God. Sorry. Yeah, I am. I am supposed to be saying something. One downside, if not, I can't see the... Yeah. So that's a kind of philosophical question. It doesn't have functions, or it actually does have functions. So, yeah, it does. Yeah, it does. Yeah. So that's a good question that we'll get into today. What it means to support recursion and why it supports recursion. But yes, it does. The functions in simple IR, I mean, they're really just the x86. System 5, we'll talk about it today, how recursion works. But yes, they do support recursion. And we'll actually see how recursion is supported when you have an assembly language. So the assembly language does not support recursion, or the way functions work in the assembly language does not have support for recursion. Simple IR has support with recursion because of the way we translate it into x86. And that's a good question because we'll actually see that today, why recursion works with our the functions in Simple IR. So what I was showing you before is we've got this CodeGen 1 project is up now, and I've given you this handbook for all the code generation projects. So it has some common stuff here. It gives you, for each project, which functions of the Antler listener that you're going to be implementing. So just quick refresher. You have a grammar for Simple IR. Let me bring that up, since I wasn't showing this on the screen. You have a grammar for Simple IR that says the pattern, the string pattern that each construct in the language looks like. So you have an assignment construct. Remember, it's some name token followed by the assignment operator followed by an operand, which is neither name or a number. And what the Antler parser does is it turns this into a parse tree, which we talked about a couple weeks ago. And Antler will walk that tree for you. And remember that translations and interpretations can be framed as just tree walking algorithms. You just walk over the tree, and each node represents one construct in the input language, and you write code in your tree walker to spit out new code for your translator. So the Antler parser framework provides features for you so that you don't have to do the hard work of doing all that tree walking and parsing. Instead, you just have a template, a code template, that you can fill in what code you want to run whenever each of these constructs is seen by the tree walking algorithm. So hopefully you saw that with the infix to postfix assignment, where we only had two constructs in our language we needed to write code for. What do you do when you see a number token, and what do you do when you see an operation token? And all you have to do is fill out the code within the listener functions. So that's what these names correspond to. This is the code that you write that will run whenever a Simple IR function is entered, whenever a Simple IR go-to statement is entered. You're going to write code there, C++ code, that will spit out assembly code whenever one of these Simple IR constructs is seen. And so this handbook is a guide to the whole compiler project. And I've linked here which functions you need to implement for which project. So for CodeGen Run, it's all the stuff around functions and function calls, function definitions and functions calls. So you go to the section here on what to do for that listener class, and it tells you what the output should look like. So when you enter a return statement, this is an example of what the assembly code will look like. This is not, remember, this is just for one program, a program that returns 10. But this is what the output will look like, for example, and it gives you a description of what your function should do when it sees a return statement, for instance. Okay, so that's the CodeGen project. Today we're going to go over functions, which is tricky because there's a lot of conventions that are used in order for our functions to integrate with the rest of the Unix toolchain that we have to be able to use the assembler and the linker with our Simple IR. Okay, so questions about anything so far? Questions about Simple IR? Questions about Antler? So this is what a parse tree looks like, and you walk the tree. So this is an interpreter tree walk. This is a translator tree walking algorithm for our infix to postfix. For our expression interpreter, our expression compiler. All right, any questions before we continue with functions? All right, let's take attendance. All right, let's get into functions. So remember that the goal of our compiler is to take programs that are written in this simple IR language, which doesn't run on our physical machine, we just kind of made it up, and translate it to x86 so that it actually will run on our physical hardware. So this is our input language, simple IR. Our output language is x86. So you'll literally just print x86 code. In the same way that your infix to postfix project, you literally just printed out postfix notation. You just said cout or print it. It's like printf. You just print it out to standard out code. And what makes the compiler a compiler is that it doesn't just print out any code. It prints out code that's going to be an equivalent program to the input. And one way to define equivalence is that if you give the same inputs to the simple IR program as you do to the x86 output program, then you get the same output for each program. As long as they're deterministic, which the languages that we're translating between are, then any input you give to the simple IR program and to the x86 program, they should have the identical outputs. That's like a definition of correctness for our compiler. So questions on that? Questions on the idea of what a compiler does? Yeah.
So this is going to be more, I guess, philosophical, but let's say you have two programs compiled for two different machines, and the program is a bit buggy, so there's a glitch where in the program you can get the program counter to somewhere where it's not supposed to be, and it starts executing stuff that's not supposed to be interpreted as machine code. And because they're compiled for two different machines, even though the instructions are equivalent, this garbage data that's being read is different.
Yeah.
So even though you have all the equivalent instructions, this glitch would cause the two programs to behave differently. So would they really be the same?
So the question was, what if you have buggy or glitchy code, or you have an exploit that changes that it's like a stack overflow attack. So the two programs, so you compile it for two machines, they ostensibly have the same sequence of instructions, but because they access data outside what the developer expected them to access, they do different things, they behave differently. So the way the C standard and other programming language designers get away from this is they just define away the problem. They say, if your code is accessing data that is not in one of the variables in the program, then it's undefined behavior. And so they say, if you have undefined behavior, the compiler can do whatever it wants in the translation. They make a joke, like it can just blow up the machine or something, or start a nuclear war or something like that, if for undefined behavior. So they just define away the problem.
The actual example of that would be, Super Mario Bros.
Super Mario Bros. 2, right?
No?
The first one. Oh, the first one. Okay, Super Mario Bros.
Glitch,
Oh, Super Mario Brothers World, right? The Super Mario. Yeah, that's right. There was a glitch where you can the end game glitch, right?
like the minus world glitch.
Oh my. Okay, yeah.
If you go the wrong place in the wrong way, then go down a pipe, it takes you to what seems like world -1. But in the original version of the game and the later re-release, even though they're identical in every way, this glitch level is different between those two versions.
I guess because of the undefined behavior of the compiler.
Level data that's not supposed to be read as level data.
Yeah, and this kind of goes back to I think my very first lecture, which is what is a bug. So in order to describe these, we have to say it's a bug, right? But to the machine doesn't care what you think is a bug, right? So that's the difference between developer expectation and user expectation. So it's kind of the same thing in compilers. What does it mean to have a bug in the compiler? Well, it means that for the defined part of the language, the compiler did something different. But for the undefined parts, it's not defined, right? So what does it mean to even have a bug? And so what ends up happening, and again, I always advertise classes. If you take my compiler construction class, we'll talk more about programming language specification and compilers. But sort of in general, some of these properties of the language, the defined behavior, like not reading outside the bounds of an array, are impossible in general to prove at compile time because of Alan Turing's famous results on decidability for Turing machines, which are a good model of physical machines. But yeah, so undefined behavior, because the compiler is allowed to do whatever they want, If your program has undefined behavior, yes, the resulting program may differ, even in the same compilation, right? You could have some probabilistic compilation, and the resulting program may differ even for the same machine, many different things. So yeah, programming language designers get around this by just defining away the problem. Even in our simple IR will also suffer from this undefined behavior as well, because we can access pointers and we can play with pointers. But it's a good, broader philosophical question. Happy to talk more about it after class. And in compilers, we talk about this, how you actually define a programming language. Here we're doing it kind of intuitively and just asserting that if it's outside the definition of the language, then the compiler can do whatever it wants, or we pretend it's not there. Checking for it is possible. You can check at runtime for these things. But yeah, we can talk more because it is an interesting and hard question. But for us, I'm not going to give you anything outside of undefined behavior. And yeah, so all this is within the bounds of the definition of the language. Okay, any other questions about the purpose of what we're doing within our, the definition of our simple IR language? Okay, so this is what our goal is. We're going to generate assembly code. And you remember the tricky part about this is we're inputting a simple IR language, so you have to understand what that does. We're outputting x86 code, so you have to understand what x86 does and what the mapping between the two is, like what equivalent x86 code looks like for IR code. But then we're also writing the compiler in a programming language. We're writing that in C++. So you have to kind of keep these three languages separate in your head, and also keep in mind that when you're writing this codegen part, you may be tempted to write code that computes the value of the IR. Like if you see 3 plus 2, you might be tempted to write code that produces 5. But our goal is really to produce x86 code that will produce 5 at runtime. And so we'll see that more as I show you the translations today. All right. And the way we're going to do it is a very mechanical way. I'm going to give you're going to basically write templates that will always be equivalent to the IR. All right. So to understand how to do translation, we first need to learn a little bit about x86 assembly. And I'm no expert in x86. I don't expect you to be, but I'm going to give you enough information for translating to x86. So the first thing, and I think you might have learned this a little bit in computer organization, right? Like assembly file layout, the different segments, data section, text segment. Who learned about this? Text segment, a little bit? Okay, maybe they didn't talk about it. Okay, so let me show you a diagram. This is from a really good website, it's off here, but it's from a really good website if you're interested in operating system development or toolchain development, this OS Dev, if you want to build your own operating system from scratch. This is a great resource for doing that. But okay, so here's our executable file. And within our executable file, there's a section for the code, which is called the text segment or the text section. And that holds the binary machine code from our assembled file. From our assembled file. That's the binary machine instructions. And data is what holds data. So you can allocate kind of global variables, what would be in C global variables, to store values in C. And when the loader runs, remember the loader takes in the executable file, puts it in memory, and then the CPU starts running at main, or at the start entry point. And what the loader does is it takes these two segments, it takes the text segment, loads it into memory, takes the data segment, loads it into memory, and then initializes a heap space and a stack space for that program. I think everyone learned about heap and stack, right? Who learned about heap and stack computer organization? I think you learned about this in computer organization. So what's the difference between the heap and the stack? What is the heap generally used for? Yeah. Dynamic memory. When you use malloc, you kind of dynamically allocate variables at runtime. What about stack? Why is the stack there? Yeah. Well, stack actually is runtime allocation as well. So this data part, this is the static compile time or load time allocation. So if you only had global variables in your C program, that would be allocated here in the data segment. The heap and the stack are actually both used for dynamic allocation. We'll learn today what the stack is used for. So it's used for function local data, and we'll see why today that is. But in our assembly file, we'll just specify which segment, which section of the memory we're talking about. And let me show you. Might as well show an example of this. So here's an example x86 assembly file. We actually just say, so any of these operations that start with a dot are pseudo ops, they're instructions to the assembler. So this is telling the assembler, okay, we're starting the text section here. This is the part where the code is going to be. And then here we've got a label, and we have a bunch of machine instructions, a bunch of assembly instructions. Okay, so variable storage. Variables in our programming language may appear in any of these segments. We could use the data segment for globally allocated stuff. We use the heap for malloc, and we use the stack for function allocated variables. But and we can also use registers for variable storage. Okay, so let's talk about functions, how function local data works. So what are functions in programming languages? Yeah. Okay, a block of code that has an input and output. Yeah, that's a pretty good definition. So it's kind of like a mini program, right? Like you define its inputs, you define its outputs. And it's interesting you didn't say named. So in C, there's given a name to these, so that's how you call it. But there are other languages that have anonymous functions, functions without names, like lambdas. If you take programming languages, you may learn about these. But yeah, you can think of it as a named or encapsulated block of code that has its own input and output. And this abstracts away computation. So we can, if you have, say, a repetitive part of a program, like you're always computing the max between two numbers, instead of writing all the assembly code or writing all the C code for that max computation, you can abstract that away into a function and just give it a name or give it a variable that holds that computation. Okay, so let's look at kind of common semantics and like a C-like language of function calls. So if we've got some function main and it calls function f somewhere in main, then the semantics of this, or the behavior of this, is that main runs line by line. When it sees f, it waits here, right? It kind of waits for f to run. So f runs line by line, and once f is done, so calls f, the flow of control transfers to f, and once f is done running, main resumes, right? Main resumes on the next line or the next instruction after f. Questions on this? I think you've all written functions. I think you know this, right? And how do values get passed? Well, main can pass in a value as a parameter, and this value gets transferred conceptually to f. So if f has some parameter x, then it's as if you've assigned x to 3, whatever main passed in. And if you want to communicate output values, you use the return. And this function will be replaced with whatever the return value is. Questions on this? So that's the semantics in a C-like language. That's the semantics or behavior of a function. So it's sort of like simulating a mathematical function where this function call is replaced with whatever the resulting value of the function is. And in terms of sequence of statements, this acts like a branch. We jump to this sequence of code and jump back once we're done computing that sequence of code. Questions on this? So I want to make sure everybody's on the same page with what a function is, what a function call looks like, kind of conceptually what functions do. So this function is frozen while the f runs, and then main resumes with the computed value of f. Questions on this? Okay, hopefully that's like obvious to everyone, I think, right? You've all seen this. Okay, so let's see how functions actually get implemented. Let's start with their state, their variables. So let's take a second to look at this function here. We've got a function g and a function f. F assigns x to 1, then it assigns y to g, and it prints out these two variables. It prints x and it prints y. Here's the definition of g. G assigns x to 2 and returns it. So the question is, what is the output of this program? So assume we call f first. What is the output of this program? Okay, so I heard 1, 2. Okay, so someone says 1, 2. Any other thoughts on what this program does? Okay, someone says 2, 2.
Nothing.
Nothing? Why nothing?
Because there's no main.
I said just assume we call f. Assume we call f. F is the entry point. We call f. Yeah, any 2, 2. Okay, so we have 1, 2, and 2, 2, and nothing. Let's assume we call main. We call f. Okay, who says 1 and 2 are the outputs? Who says 2 and 2 are the outputs? Assuming we call f first. And y is defined. All right, so, poorly there. I didn't declare y either. But okay, so let's trace this program and see what the output is. Okay, when I enter f and I assign x to 1, what's the value of x? So I'll make a table here of my variables in the program. What's the value of x here? X is 1, right? Because I assign x to 1. And now I call g. So what happens when I call g? I start running g, right? So I've got a definition of g down here. The first thing that happens when I call g is I branch to g, and I execute x equals 2. So what value? So what x is this? So how many versions of x are there? So you can define x in multiple functions. How many x's are there? Different how it's that? Well, there's 2 uses of x, but I've only declared it once, right? I've only declared it as a global. So in C, if you declare x as a global variable, what happens if 2 different functions change the value? Well, it's the same memory location. It's the same memory location. So what happens is when x equals 2 in g, is I get x redefined to 2. So then when I go to print x here, what happens? It prints 2 because I've redefined the global variable x to 2. Now g also returns x. So what value is x here when I return? It's 2. So I return 2 to here. So y becomes the value 2 because that's the value that's returned by g. So then when I print y, I also get 2. Let me All right, let me actually run this program, and I'll make it a little more complete than it is now. So I'll kind of deliberately left off this local. Actually, I can just make it a global. So let's make these all globals, and I'll define a main that calls f, and to turn this into a real C program, I'll use printf here instead. All right, I think this should work. Oh yeah, so doesn't like the fact that this is not declared, but it's just a warning. Okay, so let's run the program and see what we get. Indeed, we get 2 and 2. And so why? Because x and y are global variables. They're single memory locations that both f and g have access to. So what would I have to change in order to make this output 1 and 1? I'd have to make these right, yeah, go ahead. Make x a local variable. So if I just simply make this little change, I just make x local to both functions, and you can see there's actually 2 different declarations of x now. Well, what's going to happen? I get 1 and 2. Why is that? Because in this version of the program, each function has its own table. You can think of each function as having its own table of variables. So y is still global, but x is now local to f, and you can think of there as being a second x local to g. They have the same name, but they have different memory locations. So now when I say x equals 1, I'm assigning this x to 1. And in g, when I call g, so I set y equals to g, in here I set x equal to 2, and that sets a wholly different variable, a wholly different memory location to 2. And then when I return x, that returns 2 back to y. So then y gets assigned to 2. Print x, print y. So what's the value of x? X is 1. What's the value of y? Y is 2. Questions on this? Global versus local variables in C? Yeah. Effectively, that's how we'll implement them. We're going to implement them basically as unconditional branches. Yeah, they are go-tos. They're just go-tos. But yeah, it's a good question. Are functions just unconditional branches? Yes, they're just unconditional jumps, basically. That's what we use to get into them. This function local state is what makes them more than just a branch. So the question is, how do we have, if we have the same x, how do we have 2 different memory locations, 1 for each function? We need to do a little more than just branch. But effectively in assembly, we're going to do a branch. We're going to use the Intel call function, but that basically does a branch for you. Okay, questions on this? Questions on the difference between global and local variables? So globals, you can think of if you think of looking at a declaration and saying, well, how many memory locations are there going to be? Well, if I have 2 different declarations, at least 2 different memory locations for those. But if I have a single declaration in the global space, that's 1 memory location. Okay, so this is the version with function local state. We saw what that looked like. So how could we actually implement this in the assembly level? Well, going back to our diagram here, well, what could we do? We could take this data segment here and just make 1 variable for each x, for each function's x in our memory space. So we could just say, in the assembly file, okay, let's give f a space for its x, let's give g a space for its x. And that would work. That looks like this diagram here, right? I give a memory location for each function's local variables. So the problem is that if I say, well, let's give 1 memory location for each defined variable's memory addresses, this is going to break recursion. So instead what we want to do is we want to allocate 1 variable for each call to the function, not 1 variable to each definition of the function. So who's ever seen the static keyword in C? So some people have seen this. So what does static do? What does static do? Yeah. Yeah, it makes it persistent across function calls. What that means at the assembly level, the machine level, is you just get 1 memory location for that variable. If you don't do this, then you have every time you make a call, you get a new memory location. So let's take a look at Fibonacci. So Fibonacci is a little tricky to go through. Hopefully you're a little prepared for this. Yeah, go ahead. Yes, we're actually going to go over that next, the auto keyword in C. That's what we're actually leading to, is the auto keyword. So just as a little preview. So static means give me one memory location for this function definition. So it says whenever I define this function, give me one memory location for those variables. And that'll work, like for instance this example, that'll work for this example, right? Because we only call these functions once throughout our whole program. So let's see what happens. So let's first go over Fibonacci, a little review of the Fibonacci sequence. So the Fibonacci sequence computes this. It computes, the nth Fibonacci number is the last Fibonacci plus the Fibonacci number 2 numbers ago. Questions on the Fibonacci sequence? Kind of classic math sequence. And so here's the algorithm. Who's seen the algorithm for computing this in a CS algorithms class? Or encountered it? Really? Not many people? Okay. Well, so this is a recursive algorithm for doing it. When you're on the 0th Fibonacci number, that number is just defined to be 0. When you're on the first one, that number is defined to be 1. And then here's how we can recursively define the Fibonacci sequence. We take the n-1 Fibonacci number, compute it, we call fib to compute it. We take the n-2 Fibonacci number, we call fib to compute it. And then we just add them together. We add them together, and that's our return value. Questions on the definition of Fibonacci numbers, this program for doing it? Okay, so let's write down some of the Fibonacci numbers. So if I call fib of 0, what should I get? I should get 0. If I call fib of 1, what should I get? 1. Let me, so here's let me make sure what my code. Yeah, so this is the kind of correct version. Fib of 1. If I do fib of 2, what should I get? So here's my program. What should I get for, that's not my program. For fib of 2, what should I get? I should get 1, because it's 1 plus 0. Fib of 3, what should I get? 2, it's 1 plus 1. Fib of 4, 2 plus 1 is 3. And there are several ways to define the Fibonacci number. Sometimes I start with 0, sometimes I don't. This is 5. And so this is what I should get in a correctly implemented Fibonacci algorithm program. So I get 8 for this. Okay, so let's take a look at using the static keyword, giving one memory location for each of these variables. So we have one memory location for fn of 1, one memory location for fn of 2. And let's see what happens in this program when we run that. Okay, so I'll just keep track of the memory locations here. So here's my memory location for fn1, memory location for fn2. And I've got a little table to define what these variables are going to be. So let's call let's turn this into the static allocated one. Okay, so let's say we call fib of, let's see, 0, 1. Let's call fib of 3 and see what happens when we call fib of 3 in this implementation of the program. All right, so fib of 3, what happens when I call fib of 3? Where do I go? I go here. Is n less than or equal to 0? No. Is n equal to 1? No. It's this, right? So in order for this to work, I've got to first call fib on 2, right? I call fib on n minus 1. So I call fib on 2. So how does that work? I have to start running fib of 2. I have to pause my program, my fib of 3 here, and start running fib of 2. So what does fib of 2 do? Starts running this program. It's not 0, it's not 1. And again, I have to call fib of 1. With me so far? Questions so far? So this is like the actual sequence of statements that gets executed in this recursive program. So when I call fib of 1, it matches this base case. So this fib of 1 returns and assigns 1, replaces fib of 1 to 1. And then fn of 1 gets assigned to 1 because of this assignment. Questions so far? Everybody with me on this? All right, so the next statement after, so now I'm back in fib of 2, right? Because I finished fib of 1. So the next statement assigns fn2 to fib of 0, right? N minus 1. So n was 2, so n minus 2. Fib was 2, so n minus 2 is 0. And same thing, this gets assigned to 0, so fn of 2 gets assigned to 0. I'm still in fib of 2 now, I'm back in fib of 2. So this executes fn equals fn1 plus fn2. So what does this get replaced with? fn1 is 1, fn2 is 0. So this gets replaced with 1. And so fn gets replaced with 1. And we return 1. With me so far? So we return 1, and what happens? It replaces, so we return 1, we go back to fib of 3, and it replaces this with 1. With me so far? Replaces that with 1. So now fn of 1, this gets replaced with 1. It's the same value, but okay, that's okay. Okay, so now let's call, oh, wait a minute, I better double check this. I think I may. All right. Okay, so it replaces fn of 1 with 1. And now we go to the next line. So we're in fib n of 3. So this computes fib of 1. Fib of 1 returns 1. So it replaces fn of 2 with 1. And then this returns, and this computes fn equals fn1 plus fn2. So these are 1 and 1, 1 and 1. So this gives us 2 for fn, and this returns 2. So fib of 3 becomes 2. So this looks all good. So because fib of 3 is indeed 2, right? So let's see what happens when we do fib of 4. So let's compute fib of 4, give ourselves memory locations for fn1 and fn2. So fib of 4, same thing. It's not 0, it's not 1, so we would need to compute fn1 with fib 3. And now you might think, well, okay, fib 3 is correct, so we can just replace it in here. Let's actually trace through the whole program and see what happens when we go to run this program. So fib of 3, we first compute fn1 equals fib of n minus 1, which we're in fib 3 right now, so n minus 1 is 2. And we have to stop at this point and start computing fib of 2. Fib of 2 does the same thing. It assigns fn1 to fib of 1 because it's n minus 1. And fib of 1 doesn't make any changes to fn1, fn2. It just returns 1 immediately. And then assigns fn1 to 1. After that's done, it computes fn2. And it needs to compute fn2 of 0 because it's 2 minus 2. So this gives us 0. And it assigns fn2 to 0. And finally returns, or finally computes fn equals fn1 plus fn2. This is 1 and 0. And it ultimately returns 1. So again, fib2 gets replaced with 1, and this memory location gets reassigned to 1. So now we're back in fib of 3, and we need to compute fn2. fn2 computes fib of n minus 2, which is 1. And so this replaces fib of 1 with 1. And so now we've got fn2 being assigned to 1, and we compute fn equals fn1 plus fn2. So this is 1 and 1. And we return 1 plus 1, which is 2. So finally, fib of 3, which is correctly computed to be 2. Now, fib of 4, we're back in fib of 4, so this reassigns f of 1, fn1 to 2. Okay, with me so far, I know it's a little tedious going through this, but this is what your computer does when you write these recursive functions. So we're back in fib of 4, the function we originally wanted to compute, and we've assigned fn1 to 2, because that's the result of computing fib of 3. With me so far on here? Questions so far? Yeah.
When you said that we assign an address to each function call and not each function,
Right.
does that mean we're like putting an x86 label on each function call? So basically,
It'll be on each definition. It'll be on each. We'll see how that works out. But basically, here, what I'm going to show you is when you allocate variables by function definitions, you only give one memory space for fn1. This recursive function is not going to work out correctly. So what's going to happen is we assigned fn1 to 2 here when we called fib3 on fib4. But then we've got to call fib again to compute fn2. We've got to call fib on 2 here. And so what happens when we call fib of 2? It's the same procedure here, but what happens? We assign fn1 to be fib of 1, and that returns 1. And what happens? We blow away this value 2 and reassign it to 1. You see what happened there? We've blown away fib4's version of fn1. We've overwritten it with fib2's version of fn1. We've overwritten it with 1. And same thing with fn2. This gets overwritten with 0 because we're trying to compute fn2 and fn1 for fib2, but we wanted to hold on to the values for fib4. Well, we've blown away those values because we only used a single memory location for each of these variables. So while fib of 2 will be correct, this will correctly return 1. Once I go back to compute fib of 4 is going to try to compute fn1 plus fn2. But the problem is that fn1 is 1 from our last execution of fib2, and fn2 is 0. So we get fn3, we get fib being 1 plus 0, which is 1. You kind of see that? So if we want to have recursion, if we want to have the expectation that these variables really are local to the function, if we only assign one memory location for each variable for all executions of fib, then we don't get what we expect. What we kind of expected, or what we learned about functions, is that these variables are specific to the call of fib. not specific to each definition, not to all calls of f. So that's why the static keyword in C, it persists or preserves the value of these variables across executions of fib if you've ever used static. Okay, questions on this? Do you kind of see? I know it's tedious to trace through the recursion, although you should be able to do this as a computer scientist. You see why this happens, why we lose the state of fib4. We lose the state of fib4 because when we go to compute fib2, that overwrites fib4's fn1 variable. Questions on that? So what's the solution? The solution is what we really wanted to do was every time we had a call to this function here, we wanted to make a new memory locations for its own, this call's version of fn1 and fn2. So that way when we call fib3 and we make assignments to fn1 and fn2, we have different memory locations for these values. So that way when we've got fib3, which is 2 and 1, what was 2 and 1? So fib3 had 1 and 0 for these values. Is that right? So fib3 had 1 and 1. So fib3 set these to 1 and 1. Fib2 set these to 1 and 0. So that way when I return to fib4, it has its own memory locations for these. So we can save these as 2 and 1. You see the difference? So each call here has its own memory locations for the local variables, whereas here if we use static, we only had one memory location for the definition of the function. Recursion doesn't work correctly. Multiple calls of this function won't work correctly, or will work as we expect for functions to do. But here we made a new memory location for each call of the function. Questions on this? So this kind of variable, this kind of function local variable in C is called an auto, or an automatically allocated variable. That means that at runtime, space for this variable will be allocated automatically. The developer doesn't have to make new declarations for these variables. Instead, the compiler and the system work together to make sure that each call of this function has a new memory location for these variables. Now this auto keyword is the default. So if you just take off auto and just say int fn within a function, it is going to automatically be auto. So that's, when you write in C, that is what you're using by default. And that is what you're used to if you're writing, I think in CS1 you had to write recursion in C, right? So when you use recursion in C, you are implicitly using the auto keyword. You were using this kind of allocation of variables in C. So it was ensuring that every call to the function had its own copy of these variables, these function local variables. And so we can actually see this. If I wrote this version of fib to use the statically allocated variables. And you can see here that the Fibonacci sequence works out for a little while, but that's when I get to fib of 4 and fib of 5, these aren't correct anymore. So you can see fib of 5 is not 3, fib of 6 is not 3. This is the result here. And so we get that error, or we get that unexpected value that's revealed here by having one variable allocation for each function definition. But if I change this to auto, or just take away the keyword, then I get the right sequence. So you can see that fib of 5 is 5, fib of 6 is 8, as we expect for Fibonacci values. Just with that little change of keyword. And what that does is it just changes from static, which is one memory location for each function definition, to automatically creating new memory locations at runtime for each call to the function. Okay, questions on that intuition, questions on that difference? Yeah. Yeah, so auto's the default. So I guess another way to write this would be like this. I comment out static here. You could comment out static, and it would be the same thing. So there's fib of 5, there's fib of 6, it's 5 and 8. So this is the default in C. They're always auto, yeah, if you don't put a qualifier.
So static, when I think of static, I think back to like Java and how it makes a shared instance.
Yeah, exactly. Just like, yeah, in Java, Java and C++ also use the static keyword to mean class instead of instance. Yeah, that's variables that are on the class.
So since it's shared, it's like kind of overriding.
It's overriding the shared copy of that variable. All right, questions on this? So hopefully you can start to see a little of the internals about how functions need to be implemented if we want to support this kind of function local state that we're used to in C. Okay, so the main trick to doing this is to use the stack. So this is what the stack is for. The stack is used to automatically allocate variables in memory at runtime so that functions will have local state. Okay, and the way this works is with the stack frame. So what it does is at runtime, whenever the function is called, before it's called, and during the call, the two functions will work together to allocate memory on the stack. It'll push values on the stack. And why a stack? A stack is first in, last out, right? So if we've got multiple function calls, like this Fibonacci sequence here, because functions pause and wait for the called function to finish, we know that once that called function is finished, that state is gone. We can pop that state off the stack. So if you look here, if we've got, say, fib2 here, has its own memory location, we can represent these local variables as a stack of variables for each call. So once let me actually show it as a stack. So when I call fib of 4, the next thing I do is I call fib of 3, and fib of 3 will call fib of 2, fib of 2 will call fib of 1, and once fib of 1 is done, we can just pop its local variables off the stack. Once fib of 2 is done, pop it off the stack. Once fib of 3 is done, pop it off the stack. And so because of the behavior of functions, because they wait for the called function to return, a stack is an ideal data structure for this. Because once the function call is done, we no longer need the function state in C-like imperative languages, and we can just pop them off the stack. So the call stack, the call trace, looks like a stack. Okay, so we're going to use the stack for this. Let me illustrate. Let me skip this. Okay, so yeah, I think we already went over this quite a bit. Went over this. All right. So the idea is we're going to have this stack in memory of function local variables whenever we have a new call. So fib4, once fib4 and fib3 returns, fib4 is going to call fib2. Fib2 is going to call fib1. Once fib1 is done, we just remove its local variables off the stack. Once fib2 is done, remove it off the stack. And then fib4 will eventually also finish. We'll pop that off the stack. So to do this at runtime, remember, we can't do this, we're not going to be able to do this at compile time, because at compile time we have each call of the function defined, each function defined, but if you look at our definition of fib, we've only got 2 calls here. The reason there are more than 2 calls is because of recursion. So generally speaking, you won't be able to compute how many calls you're going to need at compile time in general, because you don't know what n the user is going to give at runtime. So it'll be difficult or impossible to compute how many calls there are. This function only has one definition of fib and only 3 calls to fib. So we can't just allocate 3 spaces. So we use a stack. So we need to generate code that's going to allocate this stack space at runtime for us. So this is the difference between compile time and runtime. The compiler is not going to try to figure out or try to actually make space on the stack. Instead, it's going to generate code that will make space on the stack. And the way we're going to track this at runtime is with a register called the base pointer. We're going to keep a special register at all times during the execution of the program that's going to hold a pointer to the function's local variables at runtime. On Intel, the Intel world, this is called the BP register. R just means it's a 64-bit one, but BP stands for base pointer. And so the way this is going to work is if this is our stack frame, again, actually let's leave that in place. If this is our stack and fib4 calls fib3, we're going to have a pointer held in a register that points to the stack frame. And when we call a new function, that pointer is going to be updated to point to the currently executing function. And so when fib3 calls fib2, we're going to update that pointer to point to fib2. Make sense? So we're going to keep a register at runtime that will always hold the value of the, will always hold a pointer to the currently executing function's local variables, called the stack frame. So the trick is, how do we generate code that's going to do this for us? Because we won't necessarily know exactly the addresses in memory. How are we going to execute code that's going to do this for us? Okay, so why is this? Okay, so now we have a way to keep track of function local variables. We use a stack, and we maintain a pointer at runtime that points to the currently active function. The next problem is, though, how do we get back to the prior function's stack frame? Now, we could assume here that each function has the same size, like in fib, but we might have mutually recursive functions with different sizes. So the way we solve this, at least in the Intel world, is in addition to storing local variables, we also store the old pointer to the previous function call. So in addition to fib's local variables, we also store its old base pointer. So that way, when we're calling, we also store the old base pointer. So that way when we're calling fib2 and we need to get back to fib3, this old base pointer will preserve the pointer to the previous stack call. So for instance, when I'm in fib1, I have the old base pointer stored in memory pointing to the previous stack frame. So that way when I overwrite this register, there's only a single register, and the way when I overwrite this register and I need to restore the old function, I can just look in the stack frame to see what the old pointer was. So when I am finished with fib of 1, I can take this old base pointer and use it to restore the previous function's base pointer. And finally, the last thing I need to be able to do is to be able to branch back to the calling function. So here, when I call fib here, I am effectively branching to the top of this fib function. And in the machine, what's the register called that holds the program counter? That holds the program counter. Well, program counter, I gave you the name of it. In the Intel world, it's called instruction pointer, IP pointer. And so that holds a pointer to the currently executing instruction in memory, right? So if I branch, I don't know where I branched from. I've lost the previous program counter or the previous instruction. So the last thing I need to be able to store and need to be able to record is the last place I left off in the calling function. So here, in my first example here, how can I branch when I return? How can I branch back to here? Well, here, when I update the instruction pointer to this instruction, how do I know where I jump back to in main or in the previous function? And the way we solve that is also by storing in memory the return address of the last function call. So if I call fib of 4, fib of 4 calls fib of 3, I store the old base pointer, which tells me how to get to the calling function, and I store the return address, which is going to point to the instruction that I left off in fib of 4. Okay, so this is how I'm going to save both the previous function's local variables and also save where I need to branch back to in order to resume executing that function. So the way I'm going to do this is before I actually call the function, I'm going to store my function's return address and save the old base pointer. And so to resume, I'm going to do the opposite. When I am finished running a function, I'm going to restore the old base pointer so I have access to the function local variables, and then I'm going to branch back to that return address. All right, so I'm just going to go over this, and then we'll see some examples once I get through all this. So the next thing you need to be able to do in order to simulate how a function works is to be able to pass parameters. This is all just by convention, so we're going to be using the Unix world's, it's called the System 5 convention for this. And the way it's going to work is we're going to pass some parameters in registers, and we're going to pass some on the stack. And I'll just kind of go over what this layout looks like. So here is I took it from this website here. So here's what our stack frame will look like with all this information stored in it. So here's the example function. It defines 6 parameters and returns some value. So this is just a convention, the System 5 convention. The first 6 parameters are going to be passed in registers. So when I call this function, the first 6 parameters will be passed in registers, and the remaining 2 will be passed on the stack. We save the return address here on the stack, and then save the old base pointer. Finally, we can allocate the local variables for this function. So this function has 3 local variables, x, x, y, y, and z, z. And so here are those 3 local variables. This RBP, this is the base pointer that points to the current stack frame for the current function. And so this is how we're going to be able to this is how we're going to be able to implement functions that support recursion, that have function local state in the machine. So by using the stack. So the stack will not only store the local variables, but it'll also store any parameters that we need, the return address, and the old base pointer. Okay, questions on this? I know there's a lot of information. Yeah, sorry.
Why exactly is, out of the 8 parameters that were passed, why do 6 get stored?
So this is just a design decision by the designers of this calling convention, of the ABI. The 32-bit x86 one, all the variables were passed on the stack. But the 64-bit developers, or 64-bit ABI designers, passed the first 6 on registers. So there's a good question. Why would you? So you can do both. So what's the trade-off? What's the advantage? So what's the advantage of using registers instead of the stack for storing values in general? What's that? Faster, right? It's faster. So if you have to use memory operations to pass all parameters, then it takes more time to do a memory access than it does to do a register access. Why 6 instead of, say, 100? Well, there aren't 100 registers in the 64-bit, or at least not publicly available ones. You don't have 100 registers. Why 6 instead of 8 or 2? I think the designers probably looked at functions in the wild and were like, well, most functions are 6 or fewer, so it's going to be, most functions are going to be passed in registers, but we also don't kind of have to waste registers that can be used by the caller. So, you have a finite number of registers. You have to make a resource allocation decision about how to use them. Do you want to use them to hold variables? Do you want to use them to pass parameters? And so I think the designers probably just balance these trade-offs. But this is just a convention. You could write your own convention to call your own functions and do it a different way. But this is the convention that's used by the Unix world for Intel 64-bit chips. And so we're going to follow that so the rest of our, for instance, library all the C library will be able to actually call those. So we'll be able to call like printf and malloc and stuff like that. We can actually call these functions. And main can call, we can be called by other C functions. Okay, other questions on how we kind of overall implement functions in a machine? Yeah. So for instance, if the calling function, so the benefit of registers that they're faster, and so if you can avoid, so even though we've allocated memory locations for variables, if we could just use registers only for variables in our function, so for instance, say we only have like 3 variables, we could always store them in registers through all execution. If we have function calls where we need to pass values as registers, well, there's fewer registers for us, for our function, to be able to store variables in. So yeah, so that's the reason. So if for instance, we were using RDX in our function, when we have to call a function that has 4 parameters, well, now we have to give up that register. And we have to save it back. We have to spill it back into memory and save its value. So yeah, that's the trade-off for variables. All right. Okay. So this is the overview of this. Let me just show so I'll just sort of preview how we're going to actually achieve this with our compiler, with the support that the Intel chipset, the Intel instruction set gives us for dealing with functions. So there's a special register, the base pointer register, which is reserved for holding the stack frame, holding this location in memory of the function data. It gives us a stack pointer, which is how we can see what's on our stack. It gives us push and pop instructions for pushing and popping data from the stack. And it gives us call and return functions. And the important part to note here is that even though this is called a call, it's not a function call like a C function. Because all it does, it really just is a sort of a mnemonic for 2 instructions. It just saves the return address, which is the IP instruction pointer. It saves the return address onto the stack and then just branches. So a function call in the Intel world is basically just a branch, an unconditional branch. And the only thing it does extra is it saves the next instruction in the current function. Return does the opposite. Return pops that instruction that was saved onto the stack and branches to it. And so if you just tried to implement functions in simple IR and C using call and return, you would end up with the same problem we have with that Fibonacci program. You'd be overwriting local data if you had allocated it at all. Because this doesn't help you at all with local variables. It doesn't help you with function local state. This fact that the next instruction is saved onto the stack, that is, in data, this is the source of a huge number of security vulnerabilities. This is where you get like the whole called stack smashing attack, stack overflows. No, stack overflow is different, but this is where you get a stack smashing attack and other kinds of security attacks where a user can take over a program to have it execute what they want, because return will actually take the next instruction off the stack, which is data, instead of hard coding it in the program. Yeah.
Threading only be handled by the operating system, or should we write a programming language that supports multiple processes?
Well, so you can definitely write a programming language that supports it. Because remember, the programming language is going to be translated to assembly code. So whatever you can do in assembly code, you can design into your language to translate to. But yeah, threading, because at least the process model on in like Unix is soon to be sequential. So if you want to have true multi-threading, where so you can do multi-threading where you explicitly you could do like multiple processes if you wanted, but to have true multi-threading on like an Intel architecture, you need the OS to basically make new processes for you and switch between them. But you can design a programming language that does that and then just translate to assembly code that uses the system to have multi-threading. Okay, 1020. Let's leave it at that. And next time we'll actually look at examples of what this function call looks like.